Everyone, and welcome to my presentation about functional programming in nanotechnology. My name is Ramtin Amit Shupani, and let's start our presentation. Functional programming is a programming style that focuses on writing pure functions, functions that produce the same output for the same input and don't cause side effects. This approach helps make software more predictable, easier to test, and less prone to bugs. Nanotechnology involves manipulating matter at an atomic or molecular scale, which demands extremely high precision and control. By combining functional programming with nanotechnology, we can develop software that is not only reliable and scalable, but also capable of accurately simulating, modeling, and controlling nanoscale devices. The strict mathematical nature of functional programming aligns well with the precision required in nanoscience. Functional programming is especially effective in systems where precision and predictability matter. In nanotechnology, even the smallest error in calculation can lead to serious consequences. In the real world, whether we are simulating atomic behavior or designing nanoscale systems, one key strength of functional programming is immutability. Data doesn't change once it's created. This helps avoid issues with shared states, which is particularly important in parallel computing environments, like when running simulations of atomic interactions. Because of this, functional code is easier to debug and generally more reliable. This is critical when working in fields like drug delivery or nanoelectronics, where accuracy and system stability aren't just important, they are essential. Functional programming works especially well in systems where both precision and predictability are critical. In the field of nanotechnology, even the slightest computational error can result in significant real-world problem. Whether we are simulating atomic behavior, modeling complex interactions, or engineering nanoscale systems. A core feature of functional programming is immutability, as I said before, and this eliminates issues caused by sharing state, and it's much more safer and consistent. That's particularly useful in nanotech applications where we often need to run bigger scales of simulations across different cores or different threads. Thanks to these characteristics, functional code is easier to debug and inherently more reliable. This makes it a stronger fit for domains like targeted drugs or working with nanoscience materials that we are trying to create. In this part, system failure or inaccuracies are not just costly but potentially dangerous. While functional programming offers real benefits, applying it to nanotechnology comes with certain challenges. First, most scientists and engineers in the field are more familiar with imperative languages like C Sharp, or like C++, which are traditionally used in embedded systems and hardware level programming. This makes the learning curve for functional program languages steeper and adoption is slower. Second, some functional language can introduce extra runtime overhead in high performance or real-time applications like nanorobotics. This added cost might be unacceptable, where speed and efficiency are non-negotiable. Lastly, many existing nanotech tools and simulation frameworks are written in imperative languages. And At first glance, functional programming and nanotechnology might seem like an unusual combination, but together they are forming a powerful partnership, one that pushes the boundaries of precision, efficiency, scalability, and modern science. As nanoengineering advances, adopting functional programming principles could unlock major improvements in simulation accuracy and reliability. Um, Thank you so much for listening to my presentation. I hope it gave you a new perspective on the nanotechnology and functional programming.